Hi everyone, good morning, welcome to the class. So this class is a continuation of the previous class on unilateral set transforms. In the previous class, we have discussed about unilateral set transform, difference between unilateral and bilateral set transforms, and we have talked about how to find unilateral set transform of signals. So we have discussed a lot of examples here, and I've given you some homeworks also. So I will share you this document also in the Telegram group after this class. Right? Now we will discuss something very important in today's class. Right. Fine. So let me start. So today we'll talk about first thing we'll talk about is solving difference equations. Okay, solving difference equations. So before talking about solving difference equations, we should know the property. One very important property. If you remember, when we are talking about unilateral Laplace transforms, we have solved differential equations with initial conditions. To use to solve the differential equation with initial condition, we have used a property of differentiation. Okay, we have used a property of differentiation in unilateral Laplace transform using initial conditions. If you remember, I'll just recollect that property once. So x of t, if Laplace transform is x of s. Now d by dt of x of t, if differentiation of x of t, then if it is a BLT, the property is s into x of s, whereas if it is ULT, the property is different. So d by dt of x of t, ULT property is, because ULT we talk about only the causal part, so that's why initial conditions are important, and that's why the property becomes little different. This is how the property will be using unilateral Laplace transform, because the property of differentiation on unilateral Laplace transform takes care of initial conditions. Initial conditions are important in unilateral Laplace transforms because in unilateral Laplace transform, we are dealing with the signal only for the positive time. So that's why whatever has happened at the 0 instant of time or just before 0 instant of time becomes very important in unilateral Laplace transform. Whereas in bilateral Laplace transform, we consider the signal for all time. So that's why initial conditions are irrelevant in bilateral Laplace transform. Right. Similarly, there is one more property here, d square x of t by dt square. Unilateral Laplace transform property is s square into x of s minus s into x of 0 plus x dash of 0. So this is the property. One second. Yeah, hi Niklesh. Give me a second. Fine. So this is the unilateral Laplace transform property on differentiation. Okay, we have used this property while solving differential equations with initial conditions, right? Fine. So what we have to similarly in discrete case, we don't have differential equations. We will be having difference equations. In difference equation, instead of differentiations, we will be having x of n minus 1, x of n minus 2 kind of terms. So the property of unilateral Z transforms will be little different from bilateral Z transforms for a signal which is shifted. So let me talk about the property. X of n, if bilateral Z transform is x of z, then x of n minus 1, the shifted version, the delayed version of x of n, if you are talking about bilateral Z transform, then it becomes z to the power of minus 1 into x of z. and x of n minus 2 bilateral z transform is z to the power of minus 2 into x of z. What we are using here is nothing but time shifting property. Okay, simple time shifting property. Right. So what if the same property is discussed in unilateral z transforms? If x of n unilateral z transform is x of z, then x of n minus 1, the delayed version of x of n, if you are talking about unilateral z transform, it will be little different. I'll prove it in the next slide. It is z power minus 1 into x of z plus x of minus 1, and x of n minus 2 unilateral z transform is z to the power of minus 2 into x of z plus x of minus 1 plus x of minus 2. I think my mistake here, small mistake I guess. I think here it should be minus only, right? All minuses only, right? Correct me if I am making any mistake. I think this should be a minus, right? Both should be minus only. Right. So this is x of minus 2. Fine. So this is the property of unilateral z transform. While you're talking about time shifting property, where it is taking care of initial conditions. And initial conditions are relevant in unilateral z transform because in unilateral z transform we are taking into consideration only the positive part of the signal or causal part of the signal. So that's why when you're using time shifting property, these initial values like x of minus 1, x of minus 2, they become important. Right. Why is this? Let me prove this for you. Okay, let me take a signal. Zero, 1, 2, 3. Let me say this is x of n, and this sample, I don't know what is that sample. I'm talking about general case. Let me say it is x of minus 2. This is x of 0, and this is x of 1, x of 2, and x of 3. As a function of n, we are having x of n. Okay. Now, for x of n, z transform is x of z. Okay, and what is x of z? We can write. Let us write this. It is x of minus 2. Let us assume the remaining values are zeros. Just for convenience, let us assume the remaining values are zeros. X of minus 2 into z square plus x, one second, unilateral z transform. We are talking about unilateral z transform. If you are talking about unilateral z transform, there is no need to consider the negative time part. Okay, sigma x of n into z to the power of minus n, n running from 0 to infinity. So substitute n equal to 0. It will be x of 0 into z to the power of minus 0 plus x of 1 into z to the power of minus 1 plus x of 2 z to the power of minus 2 plus x of 3 into z to the power of minus 3. So remaining samples, I'm assuming them as zeros, but if they are there also, you can extend the other terms also. You can write the remaining terms. Now let us talk about x of n minus 1. Understand carefully. X of n minus 1. Before finding x of n minus 1, if it is bilateral z transform, then there is no confusion at all. We could have written it as z power minus 1 of z transform of x of n. We can easily write it out. But here in unilateral z transform, we are having a different property. Why is that property? That is what I'm trying to prove here. Right. Now let me plot this as a function of n. I'm plotting it. If you plot x of n minus 1, this one is shifted towards right side by 1 unit. Whatever is at minus 2 comes to minus 1. whatever is at minus 1 goes to 0, whatever is at 0 goes to 1, whatever is at 1 goes to 2, whatever is at 2 goes to 3, and whatever is at 3 goes to 4. It is minus 1, 0, 1, 2, 3, 4. See this one? It is x of minus 2. Yes, x of minus 2 at minus 1. X of minus 1 at 0. X of 0 at 1. X of 1 at 2. X of 2 at 3. And x of 3 at 4. Observe this one. Now, let us find the Z transform using our basics only. Let us not deviate from the basics because here we are trying to prove it. So, let us go with the basics. It is equal to sigma x of n minus 1 into z to the power of minus 1, because we are trying to find the Z transform of x of n minus 1, n running from 0 to infinity. Now, if you put n equal to 0, it is x of minus 1 power of 0 plus x of 0, n equal to 1 if you put, it is x of 0 into z to the power of minus 1 plus x of 1 into z to the power of minus 2 plus x of 2 into z to the power of minus 3 plus x of 3 into z to the power of minus 4. Observe this one carefully. It is x of minus 1 plus x of, observe this one and observe this one, they are exactly same except z power minus 1 is extra. Z power minus 1 common from all these terms. What remains is x of 0 plus x of 1 into z power minus 1 plus x of 2 into z power minus 2 plus x of 3 into z power minus 3. So what you are observing here in all these terms, all these 4 terms looks like z power minus 1 into z transform of x of n. We are having an extra term here, x of minus 1, because when you are shifting towards right side, earlier for x of n, whatever is in the negative time at minus 1, that is coming to 0, and that is also being included in the z transform. Okay, that is also being included in the z transform when you are talking about unilateral z transform. But when you are talking about BZT, bilateral z transform, this will be already taken care. No, minus 2 at whatever is the sample at minus 2, minus 1, that also will be taken care already. So that's why we don't need to write anything like this. Okay, fine. But if you're talking about BZT, that's a different story already. Okay? So if you're talking about x of n, BZT, bilateral z transform, then you're going to apply the formula n running from 0 to, n running from minus infinity to plus infinity. I hope you're following. You might have understood why this x of minus 1 should be added in UZT but not in BZT. So you'll get more clarity once I do the Z transform, bilateral Z transform of x of n. If you do that, I'm finding the Z transform of this one, bilateral Z transform. Bilateral Z transform, if you find whatever is that minus 2, x of minus 2 will be the coefficient of Z square, because for n equal to minus 2, this becomes Z square plus x of minus 1 into 1 plus x of 0 plus x of 1 into z plus x of 2 into z square plus x of 3 into z cube. This is what it is. Now, how about x of n minus 1? X of n minus 1 bilateral z transform as sigma x of n minus 1 into z to the power of minus n, coming from minus infinity to plus infinity. Now substitute different value. When you substitute different values of n, generally it becomes 0. When you substitute n equal to minus 1, then the inside part becomes minus 2, and which becomes non-zero. So for n equal to minus 1, this becomes z power 1. For n equal to minus 1, it is x of minus 2 into z to the power of 1. For n equal to 0, it becomes x of minus 1 into, for n equal to 0, this is 0 here, which is z power 0, plus for n equal to 1, it becomes x of 0 into z to the power of minus 1 plus x of 1 into, you can understand the remaining terms similarly, z power minus 2, z power minus 1, z power minus 2, z power minus 3. X of 2 into z to the power of minus 3 plus x of 3 into z to the power of minus 4. Okay, right. So now if you take z power minus 1, similarly, can you guess what happens for x of n minus 2? For x of n minus 2, if you are trying to find the unilateral Z transform, it is sigma x of n minus 2, you have to find the unilateral Z transform. So n running from 0 to infinity. Now if you substitute n equal to 0, it becomes x of minus 2 into z to the power of plus 2. Sorry, for n equal to 0, it is z bar 0, right? Plus x of minus 1 into z to the power of minus 1 plus x of 0 into z to the power of minus 2 plus x of 1 into z to the power of minus 3 plus x of 2, 1 second, I don't know if this is visible or not. Let me write this, plus x of 1 into z to the power of minus 3 plus x of 2 into z to the power of minus 4 plus x of 3 into z to the power of minus 1. Now observe carefully. So it is x of minus 2 plus x of minus 1 into z to the power of minus 1 plus the remaining part. If you observe, z power minus 2, if you take common, it is looking exactly like x of z. Observe this one, z power minus 2 into x of z. Only this part was there in bilateral Z transform for time shifting property. But these two terms are extra because when you're shifting towards right side, two samples which are in the negative time, they are coming into the positive time. So that's why to accommodate those two samples which are coming from negative time to positive time because of time shifting towards right side, we are adding these two terms. That is how we got the property. I believe it is clear till this point. So this is the property I was trying to prove. Is that okay? Fine. Yeah. I was not getting your chats actually till now, so I have refreshed. Now only I am getting it. Anyway. Niklesh, you are asking how to remember, right? So don't remember anything, okay? Unilateral Z transforms are same as bilateral Z transform. If you have attended yesterday's class, I told you how to get unilateral Z transforms from bilateral Z transforms. Only thing you need to remember is this property. In Z transform, you need to remember this property, only this property, very simple property. Apart from this, there is nothing else to remember in unilateral Z transform. Everything you can get it from bilateral Z transforms. Okay, fine. Having known this property now, let us talk about solving difference equation. For solving difference equation only we have learned this, right? So now let us solve the difference. Let us put our concept into use now. Solve a difference equation. Solve a difference equation. Y of n minus 4 into y of n minus 1 plus three into y of n minus 2 is equal to 4 into x of n minus 1. Okay, to make it easier, I'll write like this. Okay, so this is the difference equation, and or they can also ask you find the output y of n. Simply, instead of asking solve the difference equation, they'll ask you by giving difference equation, they'll give the input and they'll ask you to find the output also. That is another way of asking the question. And y of minus 1 is equal to 2 and y of minus 2 is equal to minus 1 and x of n is equal to u of n. X of n is equal to u of n. This is the given data. They have given initial condition, difference equation. So now let us solve the difference equation. If you remember, we have solved a differential equation. In the same manner, we can solve the difference equation also. One second. Okay. YouTube actually this is too much of data consuming actually. From my side, from teaching side, it is a lot of data consuming actually. So for me, for one class, it is taking more than 2 GB. YouTube class. Fine. So let us solve this one. So same basics that we have discussed in unilateral Laplace transform, how to solve differential equations. Similar manner, we have to solve the difference equations also. Let us do it. You can do parallelly with me, or if you are having any confusions, just look at the slides and just follow me. Now, so let us apply the z transform on both sides for this term. So it is y of z minus 4 into z to the power of minus 1 into y of z plus 3 into z to the power of minus 2 into y of z is equal to 4 into z to the power of minus 1 into x of z. Okay. And if you take y of, no, my mistake here. I have not used the unilateral z transform property, right? I have to use that because initial conditions are given. If initial conditions are not given, then you could use the time shifting property of bilateral z transform. So here we have to use the time shifting property of unilateral z transform. Y of n minus 1 z transform, unilateral z transform property is z bar minus 1 into y of z plus 3 into z to the power of minus 2 into y of plus z to the power of minus 1 into y of minus 1 plus y of minus 2. I hope you remember this property. Oh my god, I've written a mistake here. I've written a mistake here, but we have proved it correctly only. But we have written a mistake while I'm writing the property. It is z bar minus 1 into x of minus 1 plus x of minus 2. So the order should decrease. The order should decrease. In the proof, we got it correctly. X of z bar minus 2 into x of z plus x of minus 1 into z bar minus 1 plus x of minus 2. In the proof, we got it correctly only. Right? So, yeah, we have written it correctly only here. So it is equal to, on the right hand side, what is the property? It is 4 into z to the power of minus 1 into x of z plus x of minus 1. So one thing you have to observe is they will not give any initial conditions for the input, because input means generally it is when we apply it will start, right? Output means it might be because of some past applied inputs also. Let's say there is some kind of capacitor kind of elements. What happens is some kind of past voltage or current will be stored, right? So output there will be some initial conditions, but generally nobody will give you the initial conditions for the input. Right. Now, there are two cases here. If you remember, we have discussed the similar things. There are two types of outputs here. Or we can directly find the output as it is without knowing zero input response and zero state response. We can find the output directly. Or it's better to find separately zero state response, and zero input response. There are two types of outputs that we get here. Zero state response means initial conditions are zero. Zero state means initially it is at zero state, which means there are no initial conditions. Okay, so when you're talking about zero state response, though initial conditions are given, take them as zero and solve this. Okay, in the next one where we talk about zero input response, here we make input to be zero. Though input is not zero, input is assumed to be zero. If you find the output, so the output is only because of initial conditions. When you are talking about zero input response, it is the response or output because of only initial conditions. And here zero state response means that it is the output only because of applied input, not because of initial conditions. Yeah. Fine. So let us do it. So initial conditions, though they are given, don't consider the initial conditions when you are talking about zero state response, and consider only the input. So it is y of z minus 4 into z to the power of minus 1 into y of z, plus we are assuming the initial condition is 0, plus 3z to the power of minus 2 into y of z, plus z power minus 1 into 0 plus 0 is equal to 4 into z to the power of minus 1 into x of z. Now if you take y of z common here, what remains is 1 minus 4 into z to the power of minus 1 plus 3 times z to the power of minus 2 is equal to 4 times z to the power of minus 1 into x of z. Y of z is equal to 4z to the power of minus 1 divided by 1 minus 4z power minus 1 plus 3z power minus 2 into x of n is given, right? X of n is u of n, means x of z is z by z minus 1, or 1 by 1 minus z power minus 1. Okay, fine. So let us find the z transform of this one. So it is in the denominator, it is z square minus 4z plus 3 into z minus 1, and here this z power minus 1 we can write as 1 by z, z and z cancelled, so the z square from the denominator comes to the numerator, it becomes 4z square. Okay, correct me if I made any mistake. Right, now if you can find the inverse z transform, we get the required thing. So y of z, if you want to find the inverse z transform, you have to write the partial fractions. So z1z, put it outside whenever you're taking partial fractions for the z transform. So put 1z outside. You'll understand why we have to put that 1z outside before taking partial fraction. So this z square minus 4z plus 3 we can write as z minus 3 into z minus 1 into z minus 1. So this is equal to, so what is this? So this is z into, can you tell me the coefficients here? Z minus 1 plus z minus 1 whole square plus z minus 3. Okay, you can find these coefficients maybe later. You can use your basics of partial fractions to find the coefficients. Now we have the coefficients, so we can find the output right here. Y of n is equal to, the inverse z transform of this one is, now you will understand why we have to put this one z outside, then it will be looking like a known z transform. Z by z minus 1 z transform, we know it. What is that? It is a into, it is the z transform of u of n. Because we are talking about unilateral z transforms, we assume that we are talking about only right-sided signals or causal signals. Right? Plus b into z by z minus 1 whole square is the z transform of r of n. Right? C into z by z minus 3 inverse z transform is 3 power n into u of n. What we got here is, what we got here is forced response. We can also call this as forced response or zero state response. Forced, why are we calling it as forced response? Because we are forcing the output by applying the input. By applying the input, we are trying to force the output. So that's what we are also calling, we also call zero state response as a forced response. Okay. Similarly, let us find the zero input response. So when you're talking about zero input response, let us write this one again. So y of z minus 3 into z to the power of minus 1 into y of z plus y of minus 1. What is y of minus 1? Y of minus 1 is 2. I'm substituting it here. Sorry, this is 4, right? This is 4 plus y of minus 1 is 2 plus 3 into z to the power of minus 2 into y of z plus z power minus 1 into y of minus 1, which is 2, plus y of minus 2. Y of minus 2 is minus 1, I think, is equal to 3 into minus 4 and 3, and here it is 4. Okay. Once again, I almost forgot that here it will not be visible. This is equal to 4 into z to the power of minus 1 into x of z plus x of minus 1. So let us substitute this one. So it is y of z minus 4 into z to the power of minus 1 into y of 2. 4 2 0, 8 is there, minus 8 plus 3z to the power of minus 2 into y of z plus 3 2 0, 6 z to the power of minus 1 and 3 minus 3 into minus 1 is minus 3, and this is equal to input is 0. So on the right hand side the total thing is 0 because we're talking about 0 input response. Though input is given, you assume input is 0 and find the output. So whatever output we're going to get here is because of the initial conditions. So we are substituting the initial conditions as they are given. So now if you take y of z common, it is 1 minus 4z power minus 1 plus 3z to the power of minus 2 is equal to, on the right hand side it is minus 6z to the power of minus 1, minus 3 and minus 8 combined, it is minus 11. On to the other side becomes plus 11. Okay, yeah. So y of z is equal to minus 6z power minus 1 plus 11 divided by 1 minus 4z power minus 1 plus 3z to the power of minus 2. It is minus 6 plus z into z divided by z square minus 4z to the power of minus 1 plus 3, which we can also write it as z aside 4z. So always you write positive powers of z, then only it will be easy for you to find the partial fractions. Then negative powers, positive powers are more comfortable to find partial fractions, right? So it is minus 6 divided by z minus 3 into z minus 1. Now you can find this one. So z aside, you can find the partial fractions. Z minus 3 plus z minus 1. So you can find the partial fractions easily. So once you know y of z, you can find y of n as the inverse z transform. Inverse z transform of z by z minus 3 is a into 3 to the power of n into u of n. It is u of n because you are assuming by default we are dealing with causal segments. There is no extra information saying that it is non-causal or anything else. So that's why we can assume it is causal segments. No extra information is given. Into 1 power n into u of n. Yes. So this is what? This is zero input response we can call, or we can also call it as natural response. Natural response. Finally, total output is equal to, total output y of t is equal to forced response or zero input response plus natural response, or we can also call it as zero stimulus plus zero input response. You can just add the results that we got previously, you'll get the total. You just add this result and add this answer, both y of n's if you add, that is that will be the final answer. The output because of initial conditions as well as the output because of the input applied. So this is how we can solve the difference equations with initial conditions. Fine, I hope it is clear till this point. Yeah, 43. Okay. 1 second. It's not 11. Is it not 11? And how much is that? minus 3 minus 8 minus 11 onto the other side, it is plus 11. Oh, 11z, right? Yeah. Thank you. Yeah. Minus 6 plus 11z. Yeah. 11z minus 6. 11z minus 6. Yeah, that's fine. No, now it should be fine, right? You can find A and B. Yeah, very good, Bhargavi. So it is A is minus 5 by 2 here and B is 27 by 2. Very good. Fine now, Shakya, Muskan. Right, so you can write the output, right? Now, fine then. So we've discussed about solving difference equations with initial conditions. Next, we'll talk about initial value theorem and final value theorem on the same lens as Laplace transform. So we can talk about that. Okay. Right then. So let us talk about the next part. Initial value theorem and final value theorem. So first let us talk about, okay, fine. We'll talk about initial value theorem first. Initial value theorem. So what is the purpose of initial value theorem? So initial value theorem we can use without actually knowing the time signal. We can find the initial values, means x of 0. Okay, don't think that initial value means it's x of minus 1 or x of minus 2. No. X of 0 is what we call as initial value. Using initial value theorem, you can find small x of 0 without actually small x of n equal to 0 we can find without actually knowing x of n. If you know x of n, anybody can find x of n equal to 0. But without knowing x of n, if you know z transform, then how to find the initial value, right? So that is the funda here. So let us recollect some basics here. If you remember, differentiation property d by dt of x of t property in Laplace transform is s into x of s, right? Similarly, instead of differentiation, we have something called difference in discrete case. Similar things. Similar thing to differentiation is difference in discrete case. So if you find the z transform of this one, what we get is 1 minus z to the power of minus 1 into x of z. So this is what we are going to use here. If you remember initial value theorem of Laplace transforms, I'll just write the initial value theorem of Laplace transform just for your revision sake. Limit s tends to infinity s into x of s. Right. So if you find this, this is what will give you x of 0. Next, final value theorem. Coming to final value theorem, limit s tends to 0 s into x of s. This will give you x of infinity. Final value, x of t equal to 0 and x of t equal to infinity values you can find using initial value theorem and final value theorem. This is what is continuous time case. So this is what we have discussed in Laplace transforms, unilateral Laplace transforms. Similar thing in Z transforms is instead of s we will be having 1 minus z bar minus 1 into x of z. This is what is the function that we will use for evaluating the initial value theorem and final value theorem. Right. Just recollect one more thing here. While applying initial value theorem, what is the condition under which we can apply initial value theorem? We have discussed a condition, if you remember. What is the condition under which we can apply initial value theorem for a Laplace transform? Order of numerator and order of denominator, correct? Order of numerator should be less than order of denominator of x of s. Only x of s if we consider. Order of numerator of x of s should be less than order of denominator of x of s. I told you the reason also why this condition should be satisfied. If this condition is not satisfied, if let's say the numerator order is same as denominator, then if you're finding inverse Laplace transform, you'll be getting impulse kind of functions, del of t kind of functions. If the order is more, you might get a del dash of t kind of functions, which will give you undefined values at 0 time. So since you are having undefined values for that kind of signals, so initial value theorem is not applicable for those kind of signals. Right? So final value theorem, the condition is poles, all poles, strictly all poles of not x of s, just understand it as s into x of s, should be in the left half of S plane. Should be in the left half of S plane. Left half of S plane. Now, just match them with the discrete case or Z transform. We know the relation between Z and S. It is e power STS. Okay. When you're putting S equal to 0, S equal to 0 corresponds to Z equal to e power 0, which is 1. Okay. As S tends to 0, Z tends to 1. Similarly, as S tends to infinity, Z also tends to infinity. Okay. Now we have understood in initial value theorem and final value theorem of Z transforms what we should tend Z to. In Laplace transform, we are tending S to infinity and 0. So correspondingly, we will tend Z to infinity and 1. Right. Next, the condition for initial value theorem. Whatever is the condition for initial value theorem here? Similar condition will be there, but I'll explain that condition once again. Similar condition will be there. Coming to final value theorem, poles of S into x of s should be strictly in the left half of S plane. Right. So left half of S plane means S is negative. Real part of S is negative. Real part of S is negative means you're talking about points inside the unit circle. Left half of S plane matches on to, if you compare S plane and Z plane, left half of S plane matches with inside of unit circle. Inside of unit circle. Right? Yes. Fine, very good. So just compare them, it will be very easy to remember. So whatever concept we discussed for initial value theorem and final value theorem of Laplace transforms, similar concept we can discuss for Z transform. Everything is comparison, it's much more easy to remember. Now let us talk about the actual theorem now. X of n equal to 0, initial value theorem. Initial value theorem. What should we take? The function, it's not just x of z, it is 1 minus z to the power of minus 1 into x of z, right? Now what should z tend to? Initial value theorem in Laplace transform, it was s is tending to infinity. If s was tending to infinity, z was tending to infinity. If z was tending to infinity, what happens to z bar minus 1? Can you tell me? Z bar minus 1, 1 by z tends to 0. Correct? Right. Now coming back. So s should be tending to infinity in initial value theorem. So if s is tending to infinity, z equal to e power st if you apply, z also should tend to infinity. If z is tending to infinity, can you tell me what is z bar minus 1? Limit z tends to infinity. Z bar minus 1 is 0. 1 minus 0 is 1. So you can simply write it as x of z. Instead of 1 minus z bar minus 1 into x of z, you can simply write as limit z tends to infinity x of z itself. These two functions are exactly same. Right. Next, coming to final value theorem. X of n equal to infinity. Okay, x of n equal to the final value of the signal. The value of the signal at n equal to infinity, if they're asking. And how do you find that? Limit 1 minus z to the power of minus 1 into x of z, and z should tend to final value theorem means s is tending to 0. If s is tending to 0, z should tend to 1. If s equal to 0, z is equal to 1. In final value theorem, we are tending s to 0, which means we should tend z to 1. Z should be tending to 1. If you substitute z equal to 1, you may think that it is becoming 0. No? Z should be tending to 1. Yeah, it is becoming 0, right? But in x of z, there might be something in the denominator which will cancel this term. If there is no term which is cancelled this term, definitely it will become 0. If there is a term that is cancelling out, then definitely this may not become 0. This will become some other finite value. If there is no term cancelling this 1 minus z power minus 1 in x of z, then definitely it will become 0. Right? So this is the final value theorem. Now we have to understand under what conditions we can apply final value theorem and what conditions we can apply initial value theorem. Let us write that. For final value theorem application, the condition is very simple and straightforward. For final value theorem in Laplace transform, the poles should be in the left half of a plane. So because poles in the left half of a plane correspond to exponentially decreasing signals, which means final value will be very easy to understand. Whereas for signals with poles on geometric axis or on the right half of a plane, what happens? They are exponentially increasing signals. Or if the poles are on the geometric axis, it corresponds to cos and sine signals whose final value is undeterministic. If the poles are on the geometric axis or on the right half of a plane for s into x of s, then it means that final value will be some kind of undefined value or undeterministic value. So that's why final value theorem is not applicable for signals with poles in the right half of the plane or on the geometric axis. Right. So that's why strictly poles should be in the left half of the plane in Laplace transform case or continuous time case. Whereas for discrete case, left half of a plane matches to inside of unit circle. Or we also know that for a causal signal, if the poles are inside the unit circle, then we know that it is absolutely integrable signal. Right? Similar concept here also. So if the poles are inside the unit circle, that means we talk about exponentially decreasing kind of signals. If the poles are outside the unit circle, we talk about causal signals. Causal signals with poles outside the unit circle, they will be then generally exponentially increasing signals whose final value will be undefined values. Right? So that's why strictly poles, all poles of 1 minus z to the power of minus 1 into x of z should be not just x of z. Here we are talking about 1 minus z power minus 1 into x of z. Or we can also write this as limit z tends to 1. We can write it as z minus 1 divided by z. Divided by z, just substitute z equal to 1, it becomes 1 only. So we can rewrite this function as z minus 1 into x of z. There is nothing wrong in writing like this. So all the poles of 1 minus z power minus 1 into x of z or z minus 1 into x of z should be inside the unit circle. If this happens, just check the poles of z transform. The poles of 1 minus z power minus 1 into x of z, if they are inside the unit circle, you can apply the final value theorem to find the final value. Without finding the inverse z transform, you can find the final value very easily using final value theorem. Next, what is the condition on initial value theorem? The condition on initial value theorem is, always remember this, initial value theorem, a Laplace transform case as well as in the z transform case, both cases, initial value theorem is applicable only for causal signals. Is applicable for only causal signals. For non-causal signals, you cannot apply. Which means if they give you some kind of signal like u of n plus 3 or some kind of signal which starts much before 0 time, for that kind of signals, you cannot apply initial value theorem. Which means you cannot means nobody is stopping you from applying, but even if you apply also, you will get a wrong answer. The answer will not match. So that's why you should apply initial value theorem only for signals which are causal signals, which means signals which are starting at 0 or which are starting in the positive time. Only for those signals we can apply initial value theorem. And the condition for applying is order of the numerator. Here order of numerator of x of z should be less than or equal to, less than or equal to is also fine, equal to order of denominator. I'll tell you why. Order of denominator. Whereas in Laplace case, it was little different. Order of numerator of x of s should be strictly less than order of denominator of x of s, because if the order was equal, then you'll get a constant term whose inverse Laplace transform is del of t. So del of t means undefined value. Initial value is undefined. So that's why we should have strictly order of numerator to be less than the order of denominator of x of s in Laplace case. Whereas in Z transform case, if the order was same, then what happens is you'll get a constant term whose inverse Z transform is del of n. And del of n value is defined, right? Properly defined. Del of n has a finite value. So del of t has undefined value, right? So that's the small difference. That's why here the order can be less than or equal to is also fine. Whereas in Laplace case, equal to should not be there, it should be strictly less than. If you want, I'll take an example. For example, if it is z plus 1 divided by z minus 1. So order is same, but still that is fine. No, we can write as z minus 1 plus 2 divided by z minus 1. Which is equal to 1 plus 2 into 1 divided by z minus 1. Okay. So here order is same. So you can just find the inverse z transform here. If the order is same, what happens? You can adjust the terms and you'll get a constant term. Whenever the order is same, you can write as some constant term plus some proper fraction. Proper fraction means order of the numerator is less than the order of the denominator. After making it as a proper fraction, then only you have to apply the partial fractions. Okay, without making proper fraction, you cannot apply the partial fractions, right? So this constant term will result in del of n. Del of n has perfectly defined value. Del of n height is only 1 unit. So plus 2 into, actually we should be having z by z minus. So if it is z by z minus 1, the inverse z transform is u of n. But z is not there, which means it should have been u of n minus 1. If it was u of n minus 1, z bar minus 1 will be multiplied, it becomes 1 by z minus 1. Now you can understand that it is 2 into u of n minus 1. So what is the initial value? X of 0 is equal to del of 0 plus 2 into u of minus 1, which is equal to del of 0 is 1 plus u of minus 1, u of any negative value is 0, which is equal to 1. Fine. So if you want, you can apply the initial value theorem and verify whether you are getting correctly or not. Actually, you should not do it like this. You can take the help of initial value theorem to find the initial value. But just since we want to understand what if the order is same, that's why we are taking this example. Limit term. Initial value theorem means you should tend z to infinity. X of z. Okay. It is equal to z plus 1 by z minus 1. Whenever you are tending z to infinity, make sure the function is in the format of 1 by z's. So then it will be easy to substitute and get some easily analyzable values. So if you substitute z equal to infinity, this part becomes 0, this part becomes 0, it becomes 1. And that is what we got by looking at the inverse z transform also. And since I have taken a simple function here, it was easy to find the inverse z transform. If I take a complicated function, then it's very difficult to find the inverse z transform and then find the initial value. When the function is very complicated, like maybe third order or fourth order, then if you want to find the inverse z transform, it will take at least 10 minutes. If you want to find the initial value by using inverse z transform, it will take 10 minutes. Whereas by using initial value theorem, you can hardly find it within half a minute. That is the advantage. Now you should have understood what is the condition for applying initial value theorem. Order of the numerator of x of z should be less than or equal to is also fine. What if order is more? Order of the numerator, if it is more, means when will be the order more? You tell me. U of n plus 1. When will be the order more? It is z into z, no? Z square by z minus 1. When will be the order more? The order will be more only if the signal starts much before 0 time, which means it is a non-causal signal. For a non-causal signal, initial value theorem is not applicable. For non-causal signals, it is not applicable. Initial value theorem is applicable only for causal signals. Causal signals means signals which are starting at n equal to 0 are for positive time. Fine. I hope you are following. Now let me ask you some questions quickly. Find initial and final values of Do it. First question. Yeah, Murali. So that's what I was telling you, right? So all the poles should be in the inside the unit circle. You're talking about causal system, and you're talking about all the poles to be inside. If all the poles are inside, then definitely you're talking about stable system only, right? If at all, if you're talking about system. Generally, initial value or final value is talked about for a signal, not for a system. Initial value theorem and final value theorem is talked about for a particular signal, not for a system. Okay. If you're talking about systems, impulse response, that is fine. But from your question, if I want to answer, initial value theorem, you cannot apply it for unstable system. Okay, basically we should talk about initial value or final value theorem for signals, not for systems. But from what I can understand from your meaning, so it is not applicable if the poles are in the outside of unit circle. We cannot apply. Okay, you are asking the reverse, right? Yeah, initial value theorem can be applicable irrespective of the poles. Irrespective of the pole locations, initial value theorem can be applicable. Here, poles condition is only for final value theorem, not for initial value theorem. For initial value theorem, the condition is it should be causal signal, and order of numerator and denominator will decide the applicability of initial value theorem. Whereas for final value theorem, only poles condition is there. The order of numerator and denominator does not matter for final value theorem. Okay, now I think it should be clear. Fine. So here I have understood your question a little late. I thought it was fine. But the system, you should not talk about system when you're talking about initial value and final value. The initial values of a signal, final value of a signal we're trying to find, not for a system. Okay. So can you try and tell me the answers for the first three questions? If you want to apply first initial value theorem, first see if it is applicable or not. Is it applicable? Initial value theorem is applicable or not? The first case. Final value theorem. First see if it is applicable or not applicable. Once it is applicable, then only apply it. Is it applicable here? Initial value theorem? And definitely it is applicable because order of numerator is less. So initial value theorem is applicable. Final value theorem, if you want to apply, poles should be inside the unit circle. See the poles 1 by 2, 1 by 4, minus 1 by 8. They are all, the poles with magnitude less than 1 will lie inside the unit circle. So all the poles are inside the unit circle. Next one, order of numerator is less. So initial value theorem is applicable. So final value theorem, is it applicable or not? All the poles of z minus 1 into x of z, you have to mind this. The poles of z minus 1 into x of z or 1 minus z power minus 1 into x of z should be inside the unit circle. Are they or not? If you multiply with z minus 1 or 1 minus z power minus 1, this will get cancelled. The remaining poles are definitely inside the unit circle. So that's why it is applicable. Next one, initial value theorem, not applicable because the numerator order is more than the denominator order. So which means it's a non-causal signal, we cannot apply. Next one, the poles, if you see z plus 2, it is a pole outside the unit circle. and hence we cannot apply final value theorem also. You cannot apply. So generally what it means is, if you cannot apply means, what is the meaning of not applying? It means it takes some infinite values or undefined values or undeterministic values. Generally the meaning of not applicability means if you are not able to apply the theorem, sometimes generally the values will be undetermined, undefined values, generally final value theorem. For initial value theorem applicability, the values need not be undefined values, they can be something else also. Okay, but final value theorem, generally if you are not able to apply final value theorem means generally the final value is infinity value or undefined value, because we are talking about poles outside the unit circle which are exponentially increasing signals whose final value will result in infinity value, undefined value. Right? Can anyone tell me the answer for the first question? Initial value theorem. Limit z tends to infinity, x of z, and what if you substitute? Here if you are substituting, take z cube common here, and if you divide z, if you take common here, then what happens is 1 by z square is extra, and if you substitute z equal to infinity, it becomes 0. So initial value is 0, correct? Shakya, observe the statement once. The statement is the poles of 1 minus z power minus 1 into x of z, which means one pole at z equal to 1 is acceptable. On unit circle, the one pole at z equal to 1 is okay for us if you are talking about only x of z. So that's why, to avoid confusion, I am saying poles of 1 minus z power minus 1 into x of z should be inside the unit circle. Once you multiply with 1 minus z power minus 1, if there is a pole at z equal to 1, that will get cancelled, right? Similar to s into x of s, the poles of s into x of s should be inside the unit circle. They are s equal to 0. If there is a 0, if there is a pole at s equal to 0, that gets cancelled, right? That gets cancelled because we are talking about s into x of s. I hope you are following. Here, you are talking about, your confusion is here only, I know that. So final value theorem, if you want to apply, x of infinity n equal to infinity is equal to limit z tends to 1, 1 minus z power minus 1 or z minus 1 into x of z. If you are talking about z minus 1 into x of z, it is z square by, if you cancel z minus 1, it is z minus half into z plus half. See this one? Z minus 1 into x of z, if you consider, all the poles are inside the unit circle. Okay, there can be pole at z equal to 1, one pole at z equal to 1 in x of z. So since it is one pole is acceptable, two poles are acceptable, it is confusing to remember. That's why I am telling you, remember in this way, s into x of s, pole should be in the left half of s plane. And poles of z minus 1 into x of z should be inside the unit circle, that way. Now if you substitute, what will be the answer? It is 1 by 1 minus half is half into 1 plus half is 3 by 2. And what is the answer? 4 divided by 3, correct? So here we got the final value theorem in the second question. Just to answer your question on z minus 1, I have talked about this. Next, coming to the previous question, limit z tends to 1, x of z. Can we apply? Yes, we can apply. So just substitute 1 here. 1 minus 2 divided by 1 minus half is half. 1 minus 1 by 4 is 3 by 4. 1 plus 1 by 8 is 9 by 8, which is minus 1. And this is 4 plus are 8. 8 8 is 64. Minus 64 divided by 27. Are you getting the same answer? Very good, but that's what I've explained. You missed that point, I think. See this one? It is 1 minus z. Correct. It is z minus 1 by z. But what? Z is equal to 1 only, no? Z equal to 1 only, no? So that's why it becomes z minus 1 into x of z. Okay? Fine. Is that okay? Yeah. Now let us come back to the question. First question is done. Then are you also getting the same answers? Are you getting the same answers or different? So for the second question, I got the final value. I have to find the initial value. Limit z tends to infinity. Limit z tends to infinity, x of z, which is equal to, see this one, order is different, no? So if you can take z cube outside, because whenever you want to substitute z equal to infinity, express in the form of 1 by z. So take z common from this, z cube will be outside, z square and z cube cancel, it will be z. Here it will be 1 minus 1 by z, 1 minus 1 by 2z, 1 plus 1 by 2z. If you substitute z equal to infinity, this becomes 0, 0, 0, 1, 1, 1 here, and 1 z outside, so it becomes 0. Initial value is 0, final value is 4 by 3. Last case we cannot apply. So if you cannot apply, you cannot find them, right? Yeah, Muskan. First one. Yes. I missed it actually. Yeah, thank you for reminding. When you're talking about final value, I missed this. In final value theorem, we have to multiply with z minus 1, right? For initial value theorem, there is no requirement of multiplying with z minus 1. Yes, if you multiply with z minus 1, what happens? I think the answer will be pretty straightforward here. Z minus 1 into z minus 2 divided by z minus half, z minus 1 by 4 into z plus 1 by 8. When z minus 1 does not get cancelled, in the second question, z minus 1 got cancelled, okay? In the first case, it is not getting cancelled. If that does not get cancelled, what happens? If you substitute z equal to 1, 1 minus 1 becomes 0, the result becomes 0. Yeah. I forgot to take this z minus 1. Yeah, you have to take that. And so the observation here is, if that z minus 1 is getting cancelled, then only we will get some answer as some non-zero answer. If that z minus 1 is not getting cancelled, then you will get a 0 answer. Okay? Definitely, no? You should definitely get that, right? You should definitely get the answer as 0, definitely, if the order of numerator is less. Because by using initial value theorem, you can understand. If you want, you can take an example where numerator order is less than the denominator and find the inverse Z transform and check the initial value. Okay. Fine, I hope you are understanding. No. If you want a non-zero initial value, then only numerator order is equal to denominator order. Okay. If you want a non-zero initial value 0 is perfectly defined value. Okay. 0 is a perfectly defined initial value. Or else I'll just tell you in another way. If the order of numerator is the same, then if you do division, polynomial division, if you are doing, if the order is same, then you'll get a constant term. Constant term corresponds to initial value, no? I hope you're following me. See, x square plus x plus 1, if you are dividing with some kind of x square plus 2x plus 1, if the order is same for the denominator and numerator, then what happens? When you do division, then you will get a constant term, correct? If the order is less, what happens? If you are x square plus x cube plus 1, let's say, then what happens is you will start with the x power 1, right? You will start with x power 1, there is no constant term. The constant term always corresponds to x of 0. I hope you're following. So here, if you divide the numerator with denominator, whatever is the quotient, that is what we are getting the answer, right? So the quotient part will, if it is having a constant term means the z bar 0 coefficient. Constant is nothing but z bar 0 coefficient. So that constant term will not be there if the orders are not same. Okay? Yeah. Fine then. I think you are following, Muskan. Any other questions you can ask on the Telegram group also, no problem. Sorry, you're saying something? X bar minus 1. Hi, Kuldeep. Okay, fine. So if the order is not same, if the order of numerator is less, then what happens? You'll get negative powers only. Correct? Yeah. Now I understood what you have typed. X bar minus 1, right? So you'll get negative powers. Negative powers means they are coefficients of x of 1, x of 2, x of t. You can understand it that way. I'm just trying to support the answer why the initial value is 0 if the order is different by using the general concept. Fine? Okay then, so that's it about unilateral Z transforms. We have talked about initial value and final value theorem also. So these two classes should cover all the topics of unilateral Z transforms. Fine then, so we'll meet again in the evening at 4 p.m. So at 4 p.m. we are having a special class. We'll solve some problems on NTA systems. Okay? Fine then. So our new course is starting on Wednesday. Our new course is starting on Wednesday. Sorry, not Wednesday, my mistake, Monday. Our new course on DTFT, FFT, DTFT, DFT and FFT is starting on filter design, is starting on Monday. Same timings, 3 p.m. to 5 p.m. Okay. So, fine then. So, we'll meet again in the evening class 4 p.m. And tomorrow is a Sunday, right? Tomorrow there will not be any class. And then after that we'll meet again on Monday. So if there is any YouTube class scheduled, I'll update in the group. I have not yet scheduled any other YouTube classes. There are 3 more YouTube classes I have to take this month, which I will schedule very soon, and I'll update you in the group. Fine. So the students who are having Unacademy Plus subscription can leave now. So I have to explain few things for the students who are not having subscription. Fine. Bye then. Bye Shakya. Bye Muskan. Yeah, bye Bhargavi. Okay. Yeah. Fine. So for the sake of other students, let me make a small introduction and then I'll give you some few details about the subscription part. So these are my details, and I teach 2 subjects: signals and communications. So I'm starting communications course starting from June 2nd week. Interested students can take the subscription and start attending. And if you take subscription, you are not only attending. You can not only attend my classes. You can attend the classes of every teacher available on the platform. So there are multiple extraordinary teachers available on the platform, not only for ECE, for all other branches also. Especially for ECE branch, extraordinary teachers are available. I will show you the list of faculties also. I am just showing a small list of faculty. There are many other teachers. There are many other extraordinary teachers. So you can see the teachers' names and their experiences and their expertise here. Extraordinary team of faculty is available for ECE. It's an amazing platform, an amazing team is available here to train you guys. So if you're interested, you can take subscription to learn from us. And the most important part here is the subscription fees, which is very less. So for 1 year, it's hardly 25,000. So where you get multiple benefits that you don't get in the offline coaching. In offline coaching, you cannot listen to the same subject multiple times, whereas on this platform, Unacademy platform, you can listen to the same subject multiple times, same classes multiple times, any number of times, unlimited number of times. You can listen to live classes as well as recordings also. And you can also listen to the same subject from multiple teachers also. whomever you like. You can listen to the subject from multiple teachers, which is not available in the offline platforms. And the fees that we are charging here for the quality that we provide, this is a very small fees compared to the quality that we are providing on Unacademy platform. So that too, in this phase, you can apply the code that I have provided you here. You can apply this code, and you'll get some discount of 10% here once you apply that code. So the fees comes down much more then. So the fees is very less for the quality that we provide on the platform. The fees is very less, and you can sit at the comfort of your home and you can listen to the classes. And yeah, you can listen to the classes at any time which is convenient for you. Generally, most of the classes will happen in the evening, most of them, but some classes will happen in the mornings as well as afternoons also. Whichever timing is convenient for you, in that duration of time, whichever classes are happening, you can listen to them. And whatever classes are happening in a time which is not convenient for you, those classes you can attend the recorded lectures. And same subject will happen every month from different teachers. So the same teacher will teach the same subject again every 2 or 3 months. So if you miss the live class of one teacher at certain month, don't worry, you can listen to the same classes again after a few months. Any further doubts, you can contact me. These are my contact details. These are my contact details. So this is my Telegram ID, and this is my Telegram group for a doubt clearance. Any doubts that you have regarding subscription, or any doubts you're having regarding subscription, you can contact me on this Telegram ID. Okay. And if you're having any doubts on signals and communications, you can contact me on this group. Okay. If you don't have Telegram, just install it. That is a beautiful app. And I'm also available on Facebook also. So you can follow me on Unacademy page as well, so that you'll get updates on my free classes, special classes, and YouTube classes as well. Fine then, thank you. We'll meet again in the evening at 4 p.m. I'm taking a special class, which is a free class. Anybody can attend. You can also attend. Fine. We'll meet soon. So happy learning, and we'll be waiting to teach you guys. So it's an amazing platform. So hope we will see you soon on the platform. Thank you.